So in today's lecture, I'm going to talk about the thermodynamic identities and the Maxwell relations. So we'll also be working on a couple of example problems from our text, which is Schrodinger's thermal physics. So in an earlier lecture, we discussed the thermodynamic identity, which is du is equal to TdS minus PdV plus mu dN. And in terms of equations that you should probably memorize for thermal physics or thermodynamics, this is one of them. The thermodynamic identity is a really important equation. But sometimes you might rather have this identity in terms of one of our other thermodynamic potentials, like the enthalpy H, the Helmholtz free energy F, or the Gibbs free energy G. So let's figure out what this identity would be for H. So remember here, H is U plus PV. We discussed that in a couple of previous lectures. So if we wanted to make a differential out of that, then we would do dH is equal to du plus PdV plus VdP. Okay? Now, du, that's given by the thermodynamic identity. So we plug in for du, that's TdS minus PdV plus mu dN. And then we add on, of course, the PdV plus VdP from our dH. Now, you can see that some stuff cancels out. From the du, you have a minus PdV, and then you have a plus PdV outside. And so those two things cancel. And then what you end up with is dH is TdS plus mu dN plus VdP. So there's your thermodynamic identity for the enthalpy. Now, let's do another example. Let's do F. Okay, let's do the Helmholtz. So F is U minus TS. So dF would be du minus TdS minus SdT. Yet again, plugging in with the thermodynamic identity for du, du is TdS minus PdV plus mu dN, and then we have the minus TdS and minus SdT that we had from before, from our definition of F. Now, you can see things cancel, right? The TdS cancels out with a minus TdS. And so what you end up with is dF is minus PdV plus mu dN minus SdT. So there's your thermodynamic identity for the Helmholtz free energy dF. So what you can see is if you look at these definitions, like for example the one that we had for dH, you can get some really useful partial derivatives here. So for example, you've got things that vary in the enthalpy expression dH, in the thermodynamic identity for dH. You've got the entropy varying, you've got a ds. You've got the number of particles varying, you've got a dN. And you've got the pressure varying, you've got a dP. Now if you hold two of those things constant, then the third one that you don't hold constant, that could give you a partial derivative relationship. So for example, if n and p are constant, then that would mean that the dn and the dp terms, those go away, those go to zero, and you just end up with dH is equal to TdS, which means that if you were to take the partial derivative of h with respect to s, holding n and p constant, you would get t, right? Because if you divide dH is equal to TdS both sides by ds, you get dH over ds is equal to t. So you can see how that partial derivative relationship would evolve there. Now, on the other hand, if you hold s and n constant, the ds and the dn go to zero, and then you have dH is equal to v dp, which means that if you take the partial derivative of h with respect to the pressure, holding n and s constant, you get v. And then if you hold s and p constant, you get dH is equal to mu dn, which means that if you take the partial derivative of h with respect to n, holding s and p constant, you get mu. Okay? Now, you could do very similar relationships for the other two thermodynamic identities for F and G. Okay? So what I usually do is I make you do problem 5.8 in class, which we did the other day, and you develop a thermodynamic identity for dG, and you develop the associated partial derivatives for G, right? So this is the proof, okay? So we do that one in class. Now, one important one that I want to emphasize right here is look at this definition. The partial of G with respect to N holding T and P constant is equal to mu. So what this means is that you've got a nice little definition here for your chemical potential, which is maybe sort of somewhat intuitive. It's the change in the Gibbs free energy as you add or subtract a particle. So that's kind of fun, because you're only holding things like temperature and pressure constant to get that definition. You're not holding something hard like entropy or something constant. And so it's kind of an intuitive definition. It's the Gibbs free energy per particle in a way. And and that's a new definition of the chemical potential. Okay, so let's do an example of 5.12 from Schroeder, and this introduces the idea of a Maxwell relation, which I think is important enough to break out and do as an example. Okay, so here we go. Mixed partial derivatives do not generally depend on which derivative is taken first. So, for example, the partial with respect to v holding s constant of partial u with respect to s holding v constant is going to equal to, if you switch the order, partial with respect to s holding v of partial u with respect to v holding s constant. So, if you switch the order, it doesn't matter for these partial derivatives. Now, using that idea, this equation, and the thermodynamic identity for u, prove that the partial of t with respect to v holding s constant is equal to the negative partial of p with respect to s holding v constant for fixed n. This is a non-trivial identity called a Maxwell relationship. And you can also derive analogous Maxwell relations from each of the other thermodynamic identities, h, f, and g. And for the ones that you work in this problem, you're supposed to hold n fixed. Okay, so I'm going to do an example here and show you that partial t with respect to v is minus partial p with respect to s. Okay, I'm going to do this example, and then what we usually do is in class, we work a couple of the other ones. Okay, so here we go. Let's remember our thermodynamic identity for du because we have to use it. du is equal to TdS minus PdV plus mu dn. Now, in this one, n is fixed. They're telling us to hold n fixed. So that means that dn is going to equal to 0. And our thermodynamic identity du is TdS minus PdV. Okay, now here's what we're using, right? Partial with respect to v of partial u with respect to s equals partial with respect to s of partial u with respect to v. In other words, you're switching the order in which you take the partials of s and v. Okay? So let's do the, let's see, I think I did the left-hand side first. Let's set dv equal to 0, which means we're holding v fixed, right? Partial with respect to s holding v constant, right, this part, and then divide out by ds from our thermodynamic identity, okay? So if you look at that, then that would mean that du is equal to TdS. If you divide both sides by ds, then what it would mean is partial u with respect to s holding v constant is going to give you t, right? Now, that's what you get for this, partial u with respect to s. And now you plug it in, and it's partial of t with respect to v holding s constant. So that gives you the left-hand side there of that equation would be partial t with respect to v holding s constant. Okay? I hope that's clear. If it's not, pause the video and stare at it until it makes sense. Okay. All right. Now we're going to do the right-hand side. Okay? We're going to prove this right-hand side is true. So the first step is the partial of u with respect to v holding s constant, okay? So what that means is that if you hold s constant, ds goes to 0. We're holding s fixed. And that means that we have du is equal to minus pdv, because remember, n is already fixed, okay? So then if you divide both sides by dv, you're going to have negative p. So that means that partial of u with respect to v holding s constant is equal to negative p, okay? Now you plug that in, this is now negative p, and you're doing the partial with respect to s holding v constant of negative p, and that gives you minus partial p with respect to s holding v constant. So now, since the order is unimportant, you set the left-hand side equal to the right-hand side, and you have partial t with respect to v holding s constant equals minus partial p with respect to s holding v constant. And we've proven that, okay? So this is the Maxwell relation for u for fixed n. Right, so that's an example of a Maxwell relation. All right, let's do one more. Let's do the one for enthalpy, okay? So in this problem, we're holding n fixed. So remember our thermodynamic identity for the enthalpy was dH is equal to TdS plus VdP plus mu dn. Now, dn is 0 because we're holding n fixed, so that just leaves us with TdS plus VdP. Okay, now, that means that if you look at this enthalpy relationship, dH is equal to TdS plus VdP. S and P are the things that are varying. So that's what we're taking the partials with respect to, and we're going to change the order. So our Maxwell relationship will come from this. Partial with respect to P holding S of partial with respect to S holding P constant, right? And then we vary the order on the other side of the equation. partial with respect to s holding p of partial h with respect to p holding s, okay? And that's because of this. The thermodynamic identity says that here s and p vary. So you'll notice that our Maxwell relationship for h holding n fixed is different from the one with u where we varied s and b, okay? And that comes from the partial, the thermodynamic identity, okay? Okay, now to actually derive the Maxwell relationship, I think once you get over that first hump, it's all downhill from there. But now to actually derive this, let's look at the left-hand side first again, okay? So here's our relationship. dH is TdS plus PdV, TdS plus VdP. And then what we're going to do is take the partial of h with respect to s, holding p constant, and then of course n. So what that means is that if p is constant, this second term goes to 0, right? And we're just left with dH is TdS. So that means that if you divide both sides by ds, then dH ds is equal to t. So that means that the partial of h with respect to s, holding p and n constant, is equal to t, okay? Then, after that, you plug this into here, right? So then you have partial with respect to p of partial h with respect to s, which is t. So that gives you partial of t with respect to p holding s constant. So that's our left-hand side of this Maxwell relationship. And now, let's look at the right-hand side. So on this one, right here, we're holding s fixed, okay? So that means that this term goes to 0, and we're just left with VdP, okay? So, dividing both sides out by dP, we would have dH over dP gives you V. So that means that the partial of h with respect to p holding s and n constant would be V. You then plug that V in, and you have partial with respect to s of V. So that gives you partial V with respect to s holding, that should be p constant, that's a typo, is the other side of your Maxwell relationship, okay? So now we set the right-hand side and the left-hand side equal to one another, and we have a full Maxwell relation for h. Partial t with respect to p holding s constant equals partial v with respect to s holding v constant. And that's our Maxwell relationship, okay? So those are Maxwell relations, and those are the differential relationships that we can get from the thermodynamic identities for our new thermodynamic potentials H, F, and G. But you might be sitting here going, okay, she's rattling on, and there's some math, and I can follow it, but why? Why are we doing this? This seems completely useless, okay? All right, so I think it's useful to spend just a second on this, and I'm going to quote a Reddit conversation here, so you know it's not just me telling you this stuff. So here we go. Here's some reasons why you might need to know these things, these thermodynamic relationships, and then the partial derivatives that you can get from the thermodynamic identities. I'm quoting, "If you know that a quantity is conserved in a particular process, then that's useful to know, especially if the thing's not directly measurable." And I'm thinking in terms of the enthalpy or entropy here, okay? And then another user goes on to say, "We don't really have an experimental entropy meter, but we often seek to understand how entropy or energy or something else changes if we change another parameter, x. Thus, we're immediately confronted with some variation of the entropy with respect to that parameter x under some condition, y. And that's the Maxwell relationship, and it's a boon here, okay? Also, models like equations of state are often built around these quantities, and the derivatives can give useful information like the heat capacity. So those are a whole bunch of reasons why these potentials might be useful. And this might be especially true if you're doing some kind of materials research, some sort of nanotechnology research or something, where you're working in a more applied venue and you've actually got to do an experiment with these materials. And you can hold some things constant while you do your experiment, but then what you really want to extract is some other variable. Okay? So that's when these things are useful. I hope that's somewhat clear. Okay, let's do some example problems. What I'm going to do in the homework is I'm going to work parts A and B of problem 5.14 from Schroeder, and then I'm going to turn you loose on the rest of it, and you'll work those for homework, okay? So, here we go. Problem 5.14 from Schroeder says, we can derive a completely general relationship between Cp and Cv. With the heat capacity expression from problem 3.33 in mind, first consider S to be a function of T and V and expand ds in terms of the partial derivatives, partial S with respect to T and partial S with respect to V, holding V and then T constant respectively. And note that one of these derivatives is related to C sub V, which is the heat capacity at constant volume. To bring in C sub P, the heat capacity at constant pressure, consider V to be a function of T and P and expand dV in terms of partial derivatives in a similar way. Plug this expression for dV into the result of A and then set dP equal to 0. And note that you have derived a non-trivial expression for partial S with respect to T. This derivative is related to the heat capacity at constant pressure. So you now have a formula for the difference, Cp minus Cv. So those are the parts that I'm going to work for you, and then you'll do the rest of it for homework. But first, we got to work problem 3.33 because we haven't done that before. So, what's problem 3.33? It says to use the thermodynamic identity to derive the heat capacity formula shown here. C sub V is equal to T times the partial of S with respect to T holding V constant. Okay, so we're going to use the thermodynamic identity to do this. du is TdS minus PdV plus mu dN, and we're going to hopefully remember at this point, we should all remember at this point, that our heat capacity at constant volume is partial U with respect to T holding V and N constant. Okay? Now, if V and N is constant, then looking at our thermodynamic identity, the dV and the dN terms go to 0. So that just leaves us with du is equal to TdS. Okay? So that means that we're really taking a partial derivative there, right? We're holding V and N constant and looking at partial U with respect to S. So that means that partial U is equal to T partial S. And if we plug that into our definition for the heat capacity, right? If we plug partial U is equal to T partial S in there, then we end up with the equation as shown above. Cv is equal to T partial S with respect to T holding V and N constant. So I think that's pretty straightforward. You're just plugging and chugging. But if you need a second to stare at it, then do so. Okay, now we're going to derive a similar formula for the heat capacity at constant pressure by first writing dH in terms of ds and dP and using the known relationship that the heat capacity at constant pressure is the partial of the enthalpy with respect to temperature holding the pressure constant. So this is something that you should remember at this point. It should look familiar and you should remember it. The heat capacity at constant pressure is partial H with respect to T. Okay. Now we're going to use our new thermodynamic identity here. dH is TdS plus VdP plus mu dN. Now, N and P are constant here. Okay. We're not allowing the number of particles or the pressure to vary. Enthalpy is most often used for constant pressure processes anyway. Okay. So then if P and N are constant, the dP and the dN go to 0, and you're just left with dH is TdS. So that means that partial H would be T partial S, and you plug that into your heat capacity formula up here for partial H, and you get C sub P is T partial S with respect to T, holding P and N constant. Okay? Yet again, if you need a second to stare at that, do so. Okay, so that was problem 3.33, and now we're moving on to problem 5.14. So, to remind you, it said, first consider S to be a function of T and V and expand ds in terms of the partial derivatives, partial S with respect to T and partial S with respect to V. Note that one of these derivatives is related to C sub V. Okay, so this isn't really thermodynamics so much as just straight up calculus, okay? Remember that a full differential ds would then be written out and expanded in this way. So ds is partial S with respect to T holding V constant times dt plus partial S with respect to V holding T constant times dV. That's just from calculus, okay? That's calculus. But here's what's not calculus. We've already talked about this sucker. We just did it in problem 3.33. The partial S with respect to T holding V constant, okay? That was right here, okay? C sub V over T would be partial S with respect to T holding V constant, okay? So I'm going to plug that in, all right? That would be C sub V over T dt plus partial S with respect to V holding T constant times dV. That's part A. That's all there is to it, okay? Part B says, to bring in C sub P, consider v to be a function of t and p, and expand dv in terms of partial derivatives in a similar way. Now, yet again, this is just calculus. dv would be the partial of v with respect to t holding p constant times dt plus partial v with respect to p holding t constant times dp. This is just a definition of what a differential is from calculus. There it is. Okay? All right. Now, this, okay, we're going to use. Plug this expression for dv into the result of a, set dp equal to 0, and note that you have derived a non-trivial expression for partial s with respect to t holding p constant. Okay, so here we go. This was where we were at before from part A, right? Okay, we had ds is cv over t dt plus partial s with respect to v holding t constant times dv. Now, here we go, okay? What we're doing is we're going to plug in for dv, okay, using our result from the previous slide. So we have c sub v over t times dt plus partial s with respect to v holding t constant times dv, which is partial v with respect to t holding p constant dt plus partial v with respect to p holding t constant dp. Okay, so I plugged in the curly bracket stuff from my definition of what dv is. All right, now for a constant pressure process, dp is 0. So that means that the second term here, that goes away. All right, and now we're left with ds is equal to cv over t dt plus partial s with respect to v holding t constant times partial v with respect to t holding p constant times dt. Alrighty? Okay. Now we're going to divide both sides by dt. Okay? That will give me, here's c sub p over t, right, is equal to partial s with respect to t holding p constant. Because look here, when I divide both sides by dt, then on the left-hand side, I end up with ds over dt, right? And I know that that, from my relationship from problem 3.33, right, partial s with respect to t gives me cp over t, okay? So there we have it, okay? So that's my left-hand side. Now, my right-hand side is a little easier to see. If I just divide through by dt, then the second term stays partial s with respect to v holding t constant times partial v with respect to t holding p constant, and then, of course, plus cv over t. Okay? So that's where it comes from. Okay? So once you divide through by this dt, you get this ds over dt, and that gives you the relationship for the heat capacity at constant pressure on that left-hand side. All right, now what you can do is multiply everything through by t, okay? And then move the CV stuff over to the left-hand side. So if you do that, you end up with CP minus CV, right, on the left-hand side, is equal to T times partial S with respect to V times partial V with respect to T, okay? And that's where it leaves off at part B, okay? And then you're going to work the rest of the problem for homework. Okay, I hope that's clear. I hope you followed it, enjoyed it. Make sure that if you get confused about algebra or calculus at a specific part of the video, that you pause there and stare at it until it makes sense to you. Sometimes it takes a second for things to sink in, and I totally get that. All right, I'll see you in class.